This next section leading into example 8 is going to talk about one of the things that's actually kind of a basic function of calculus, the thought of a discontinuity. So let's look at a definition here. So for any function at all, f, g, h, whatever of x, any value of x that results in division by 0. So this section we were talking about earlier where you can't have 0 in the denominator, okay? Any value of x that results in division by 0 is called a discontinuity. Okay, discontinuity, I mean, I feel like it's kind of obvious where this word comes from. The word continuous, right? So a continuous function, and dis meaning not. So something that is not continuous. So a place that there's a gap or a hole or an asymptote in the function, okay? And it's so called because the graph exists to the left and to the right, but the graph gets interrupted at this point. So it's a discontinuity, okay? There's two different types of discontinuities. The first one's called removable, okay? And sometimes you'll just see it called removable. Sometimes you'll see it called removable point. Sometimes you'll just see it called a point discontinuity. So all of these things are the same thing. So removable discontinuity, a removable point discontinuity, or just a point discontinuity, okay? They're removable. Or you have something called a non-removable discontinuity. I've never seen it called infinite before, so you can kind of skip that. It is a non-removable discontinuity, and those are places where asymptotes happen, okay? So you have removable discontinuities where you have a hole, and you have a non-removable discontinuity where you have an asymptote, okay? And I kind of like to think about it in this way. So let me draw a little graph up here. So if you've got a graph, okay, and let's say, let me zoom in a little bit, and let's say that you've got this function, right? You got this function, and your function's coming along, and all of a sudden, there's a hole, and all of a sudden we keep on going, right? So if you kind of think about it as being on the highway, right? So you're driving your car down the highway, oop, there's a pothole, and then you continue driving your car down the highway. At some point, a construction crew could come in and they could fill in the pothole with asphalt or cement or whatever it is they fill in the pothole with, but they could fill it in and then it's continuous. So this is called a removable discontinuity because there's one little small problem. Once you remove the little problem by filling it in, for instance, then the problem is gone. So it is a removable discontinuity. Okay, that's a hole, right? However, if you have an asymptote discontinuity, so let's do it like this just for the sake of my example. So let's say you've got this asymptote down here, right? And this guy's coming in this way. So it's got an asymptote. This kind of situational graph, and you can ignore my terrible art skills, but this kind of situational graph, both of these go towards negative infinity at the asymptote, okay? So you could kind of think of this as like the Grand Canyon, right? So you're coming along and then you hit the edge of the Grand Canyon, okay? And our little road crew from the first example comes along and tries to fill in the Grand Canyon as we filled in the pothole. Well, it's going to be impossible to fill in the Grand Canyon with asphalt or with cement or whatever because we simply don't have enough. So this one is called a non-removable discontinuity because there's no way to just very simply, let's put a point here and fill the gap, okay? Again, you could not fill in the Grand Canyon. I mean, I guess you could, but it would take an exorbitant amount of cement. So this one would be removable, very small problem, crew comes along, fixes it up. But when you have the Grand Canyon, you're not going to be able to remove it with just a tiny bit of cement with one small thing. So it is called a non-removable discontinuity. Okay, so hopefully that makes sense about which one is which. So let's take a look at example 8 because it's very easy to see, I think, where if you have a hole versus if you have an asymptote, okay? And the way that you're going to be able to tell this is I kind of think about it this way. If you've got your function, and normally we're only dealing with these when we deal with fractions. So if you've got your function, and let's say you have some factors, so you factored the top and you factored the bottom, okay? So you've got a couple of factors on the top. You might have 3, you might have 7, however many you have. So let's say you've got these factors on the top. If you have a factor on the top that matches a factor on the bottom, so you have like x plus 3, and you have another x plus 3 on the bottom, so something that would cancel out, if it exists on the top and it exists on the bottom, that's a hole, okay? If you have the same factor on the top and the bottom, that's a hole. Anything that you have left over in the denominator, that's a vertical asymptote, and we're going to just call those VAs from now on. So that's a vertical asymptote. So once you factor the top and factor the bottom, The ones that would cancel out are your wholes, and the ones that would be asymptotes are the ones that are left over in the denominator, okay? So the ones that cancel are your removable discontinuities, and anything that's left over in the denominator is a non-removable discontinuity, okay? So that should be pretty easy to find. This guy, just for reference, anything that's left on the top is gonna be an x-intercept, okay? You don't really need to know that right now, but it is what it is, and I would like to know if it was me. So let's take a look at A. So the first thing we're going to do with this, obviously, is factor it. The bottom's already factored, but let's factor the top. So I need things that multiply to 4, okay, that add up to -5. Excuse me. So that's going to be -4 and -1. I'm going to divide by the 2. So this is going to give me -2. And this doesn't reduce, so I'm just going to leave it alone. So the top of this function is going to be x minus 2 and 2x minus 1. And the bottom of the function is obviously x minus 2. Okay, so in looking at this function that's now been factored, notice that I have the x minus 2 and the x minus 2. One's on the top, one's on the bottom, but they match up. So that's a whole, okay? And we're going to have a whole wherever that equals 0. So x minus 2 equals 0. So x would equal 2. So we have a whole at x equals 2. Okay? There's nothing else left on the bottom, so I don't have any vertical asymptotes. Okay? So what they want me to do is find the domain of the following and find the discontinuities. Okay? Well, we've already found domain a whole bunch, so I'm just going to find the discontinuities to save time. So there's a discontinuity, so I'm going to write discontinuity, and I'm going to abbreviate. So discontinuity at x equals 2, and I'm going to classify it, okay? It is a whole, which makes this a removable point discontinuity. So that's the information they're going to want for these, okay? So there's a whole, it's at x equals 2, and it's a removable point discontinuity. Okay, so let's take a look at B. Again, factoring on the top. So now I need things that multiply to -4 that add up to 3. Okay, well, things that multiply to -4 that add up to 3 are going to be +4 and -1. Okay, again, dividing by that 2. This one goes to 2. So this function is actually x plus 2, 2x minus 1, over the x minus 2. So this time, I have an x plus 2 and an x minus 2, so those don't cancel out. So since nothing cancels with the x minus 2, the x minus 2 is a vertical asymptote. Okay, so x minus 2 equals 0, so x equals 2. So there is a discontinuity at x equals 2, which is a vertical asymptote, which is a non-removable discontinuity. Okay? Non-removable discontinuity, because it's an asymptote. So it's pretty easy, I think, to see which one is which. It's just remembering which one's removable and which one's not, right? Take a look at C. On letter C, we're going to factor the top. So I need things that multiply to -12 that add up to -4. So that's x minus 6 and x plus 2. Looking at the denominator is my difference of two squares pattern. So that's x plus 2, x minus 2. Okay, so if you notice the x plus 2's, I have one on the top and one on the bottom, so those would cancel. So that's a whole. So I'm going to do x plus 2 equals 0. So x equals -2. And hopefully you can look at that and just go, oh, okay, it's going to be 0 at -2, and you don't have to write this step down. I'm just doing it for notes purposes. So at x equals -2, so we have a discontinuity at x equals -2, okay? That's the one that matches, so it is a whole, so it is removable. Point discontinuity, okay? And I also have one. This thing doesn't cancel with anything else. This x minus 2 doesn't. So the x minus 2 is actually a vertical asymptote. Okay, so this one's a whole. This one's a vertical asymptote. So hopefully you can look at that at this point. This one was -2 to give me 0. This one's going to be +2. So x equals 2 is my asymptote. So there's also a discontinuity at x equals 2. It is a vertical asymptote, so it is non-removable. Well, let's write this down here. Non-removable. Discontinuity. Okay, so that's how you can tell when the holes happen, when the vertical asymptotes happen, and if they're removable or not.